in a hyperplane going through between margins. Okay, they try to maximize the margin. And well, of course, that's for ideal case. And last time we started talking about these overlapping cases, okay, where instead of maximizing the margin, when you have complete several case, or take a reciprocal, right, then we'll just minimize the margin. But of course, here, because we introduce arrow to allow that some cases or feature vectors go to the other class. So instead of maximizing margin, we minimize this some constant divided by margin. So here the reciprocal margin plus arrow. Okay. And only quadratic programming involved. Here we have seen this example, this graphs last time. Okay. So we allow certain just addition of these select variables to go with it for this. Well, we can say these are the support vectors, but still depends on quite a few feature vectors rather than the entire data set. Because then you know the nice thing about this algorithm is that this works well for a small data set. Right? Because it only depends on quite a few vectors. Okay? Because last time we have been through this, we talked about this. So here it's impossible to find this W and B so that this is always true, because we have this non-separable cases. Okay. Of course, it's just to introduce these select variables, and okay, we know that. Just try to make this Zi large enough. This is always satisfied. Okay? Usually, that's not what we desire to have. Right? We just have any solution so that this Zi is large enough. Okay? So usually we try to avoid this trivial solution just by penalizing this these select variables in the objective function. Actually, it's by this. Okay? Actually, this is what in this AI community, this type of objective function in support vector machine, okay, minimizing this square length of that W over 2 plus that, with this C times with this constraint. C is some kind of cost to penalize the result, the cost of this result. They call this C classification problem. Okay. So that's a name that we're going to see it later. Okay. This is called C. And against the other type is called new classification. This is Greek later. Okay. And what you have seen here, this is called C classification. Okay. New classification is different. I will put this here as 1 over n, 1 over the size of the data. And then here, they penalize right here. Okay. Instead of penalizing this, they kind of reduce the objective function by subtracting some constants over here. Let's just say that, okay? The other one is minimizing. By minimizing this, they have this introduce some constant times mu, okay? Plus 1 over n, okay? And subject to the constraint, here we have this yi of this inner product of w and x plus constant greater than or equal to this rho minus Ci. Okay. This type of problem, actually I didn't have that in our class number. So we have to talk about, I have to talk about implementation later. They implement both types of classification. One is called C-type. Okay, basically this is what we have here. Okay, that's called C-type classification problem. Okay. Anyway, so idea is try to penalize your objective function in a certain way. Okay. Minimizing this, we can obtain the result. I think I have typo. I'm going to change that. See I sub I greater than equal to 0. If variable is this xi w inner product that plus b greater than equal 1 minus the ci. It's on one side, you classify as from one class, otherwise, okay. If it's less than negative of this quantity, we have from another class, okay. So basically it's from that. That's a figure we see there, right? Okay, so here it's based on this, okay. We have this one. Okay. And we did this with algorithm anyway. So here, so we want to minimize this subject to this condition. Okay. So C is basically cost or trade-off parameter between error and margin. Okay. The implementation we'll talk about later, they term this as cost. So penalizing factors anyway. Let's try to, it's like a trade-off parameter between error and margin. Because we try to minimize the training error at the same time try to maximize the margin. But these are two conflicting goals. Okay. And C is just try to, it's kind of just give a trade-off between these two conflicting goals. Okay. But anyway, still that if you look at well in the quadratic programming, you can always solve just look at the dual problems and so forth. Okay, this QP solver, and you can see again in the solver, objective function only depends on the feature vector through the inner product again, right? Just the inner product. Okay. It's not the values of this feature vector. It's only through the inner product vector. And again, the constant b is not in this objective function of dual problem. Okay, so actually that's why here you can do this this optimization first, and then b can be dealt with separately. Okay? Anyway, let's skip some of this detail and just look at the support vector, the machine in general. The strength of that is it's good generalization in theory. So it depends only objective function in this dual problems depends only on depends on the feature vectors only through their inner products. Okay, and it's also good generalization in predicts and work well with a few training instances. Remember we say that it depends only on few support vectors, right? So it works well with some small data sets. And you can always find a globally based model, unlike neural network. And we have seen example. I've shown example last time. Neural network sometimes we trap it. We didn't find the global optimum result. And it's efficient algorithm. The last thing is about the where up to now we only talk about this linear form of this support vector machine. Okay. But with this can be translated or transformed into a nonlinear form. So it's amenable to this kernel trick. So transforming to the nonlinear problems through this this kernel trick. Okay. We're going to see that. We talk about kernel function. Okay. Now here this example. If you have nonlinear decision boundary, like this one. Well, of course, this is the one shown here is completely separable problems where you have this boundary here. This probably is support vector. Yeah, this is being drawn clearly. Maybe we just draw a line that passing through few points here. This could be a support vector. Okay. So only few points would be support vectors, and then the separating hyperplane is what would be a wonderful between. So you have nonlinear decision boundary like this. Imagine that suppose you are able to stretch this coordinate. You pull this coordinate and stretch it, make it a straight line, right? And actually that's through some kind of transformation of this kernel function transformation. Okay, so to stretch it, then this becomes a linear separable problem, right? Okay. So that's the idea of this. Okay, so use another coordinate system so that the curve becomes a line. That's it, right? It's a transformation. Okay, this is a kernel transformation. So in general, it's like this. Do this transformation. Okay. This is in between straight lines and curve. Okay. And again, remember earlier, again, we mentioned that the support vector machines optimization problem depends on feature vector only to the inner product. Okay, so it's this. Okay, if you use some certain transformation, so it only depends on this inner product of the transform variable. Okay. Under certain conditions, usually call this as regular conditions. Okay. There exists a kernel so that you have this result. Okay. Polynomial of degree d, like this, for example, and actually, the package you're going to talk about that implement this idea, you use this polynomial of this form. Okay, you do this form. Okay. It's in this form. This is gamma inner products of x, y. Okay, plus some constant, or say constant, to degree of this is plus. Okay, to degree of d. Okay. This is a polynomial degree d in that form. Okay. So just do this. Okay. And basically, all you have to just replace x, y by this, the inner products of the phi of x and phi of y, okay, through this transformation. Okay. Okay, so we have seen so far with a linear decision boundary. Okay. Generalization to become nonlinear. The basic idea is transforming your feature vector. See, this is why this AI community talk about distinction between feature space and the input space. Okay. Input space is that original variable, and the feature space is that original variable through certain transformation. Right? That means there's a transform values of this original variable. Okay. The key idea is transform your input variables to a high dimensional space, okay, to make it linear, to make life easier. Right? So actually, what you see in this high dimensional space, you have this linear, either separable or non-separable problem, but it's linear. Okay? In this high dimension, it's a straight line, okay, that separates the boundaries, and then of course, then you transform back to the original scale would be sort of like nonlinear situation. Input space, the point xi are located, and feature space would be the space of this input variable after transformation. Okay, it's called feature space. And the linear operation in the feature space is equivalent to the nonlinear operation in the input space, like the one we've seen earlier. Okay. This is not exactly that. Suppose it is like reverse kernel, right? Okay. In high dimension, you have like a separable result. Okay. And then here, back to the original space, you have this nonlinear case. Are we in this one? Not yet. Okay, and classification can become easier. Actually, in fact, will be in this high dimensional space will become a linear linear problem, right? So that's the idea of this. Okay. Look at either one of this. You have this problem. Of course, in this case, if this is the case, this is like it's completely separable case. Kind of stretch this, right? You stretch your figures and into like linear problems. So here, this is straight line separating. Right? Okay. And the situation like this, okay, you can stretch this using like the distance from origin, from the center, like some kind of distance. Okay. So distance to these points are shorter than to those points and that. So using that kind of some kind of distance transformation, we make it into this kind of separating plane. So the idea is really simple, right? Of course, the problem is how do you find this transformation? Okay. So how can you place it into a feature map? See, they always come with different names for this kind of problems. Okay. So the complex in low dimension, but not so in higher dimension. You are able to find this kernel transformation and get this result. Okay. Now here, this is yet another example. Okay. Here you have, well, in this case, well, this is ideal case. This is completely separable. Okay. Problems where you can separate this group from the other groups. Okay. Think about this by bending this using this parabola. You see this result, right? So you bend that way, you can see that you can completely classify through the straight line. Okay. Simple idea, right? Okay. So here, this is an example that we actually, just like that one, you're actually having this 6 point. I did mark number 3. Okay, it's supposed to be number 3. There's a point number 3 somewhere in here. Okay, I didn't mark it, but here this is how you would use this discriminant function would allow us to separate these two groups. Okay. So mapping it into a feature space, for example, here this is one example. This is more or less like a polynomial kernel, right? Okay. So x, suppose xi, I think this is x1 again. Typo. So this is transforming x1, x2 to this x1, x2, and x1 squared, x2 squared, x1 times x2. Second degree polynomial, okay? And you run a linear support vector machine on this transform space, the feature space instead. So as a result, the result is a nonlinear separator in the input space, right? It's a linear in the feature space, but when you map it back to the original space, you have the nonlinear separator. Okay? Like any of these cases we have seen, right? This is nonlinear separator. Separating these two groups. You still come up with some kind of infinite dimension, and usually this is done through the kernel to compute it. Okay. And this is so-called a kernel trick. That's why the name is for it. Get this. It's really good with this kernel trick that we can transform with the appropriate choice of kernels. We can transform to this to linear in high dimensional space. So here, well, this is general kind of schematic parts of this general idea. In the input space, it's nonlinear separated. Okay, and you actually transformations is like as we said always. Okay, transformation is like stretching or bending or in any way you think about, right? To make it linear. So then in the feature space, it's the linear separating line in this case. Right? And computation could be very costly because of high dimensions. Okay, so usually it's done through the kernel instead of just using the high dimension. Okay, so kernel tricks come to solve this problem instead of having this very high dimensional transformation to get some kernel. Okay. Kernel is simply just a set of functions that you can think about this as a basis of transformation. Okay? And use a combination of this kernel function to transform to this high dimension. Okay. And again, we can see that the data points or the of the input vectors appears in this objective function only through the inner product. So that's why we can do this kernel trick. Okay? As long as we can calculate the inner product in the feature space, we don't need this mapping. Right? Just do this explicit. Okay, you do this calculation in the feature space. So we just define the kernel function as this. Okay, it's through the inner products of this field xi and field. See, I have a lot of type of this xi and xj. It's xj. So, okay. So I need to make these changes. Okay. So the data appears in the training problem is in the form of their inner product. That's all you have. And actually, only quite a few of them, right? Only quite a few of these vectors will go into your optimization problem, namely the support vectors. That's why this, that's why this algorithm is quite appealing. Okay? So the idea is to transform the data, map the data to some other space using the mapping. And training algorithm now only depends on data through the inner products. Okay, after this, the mapped result. Okay. The transform data only to the inner product of transform values. Okay. So the problem is to find kernels, right? That's what we are trying to look at. Well, let's just go through ideas. Just, we don't need to delve into this the detail of the theory. Okay? Just get the basic idea. Okay. See, this original author argued that the fundamental problem of this so-called cursor dimensionality is not it's about the flexibility of the classifier, and he argued that in this method, this high dimension is not a problem. Okay, it's only how you classify it. Okay? The idea is of this support vector loss function is analog to a ridge regression, where and the idea of ridge regression is try to usually out of this regression problem is to become overfitting. So they use some kind of shrinkage parameters to control this this overfitting in this ridge regression. Have you learned this ridge regression in 662? Well, unless we use it, then let's not talk about it. Okay? We don't use it anyway. The idea is that ridge regression is try to eliminate, try to simplify the models. Okay, so in a sense, the ridge regression try to penalize overfitting. So try to come up with a simpler model rather than a complex model. Okay. The most tricky part of this support vector machine, of course, is the choice of kernel. Right? The theory said that you can find that. Okay. But how can we find it? Okay, is the kernel you use good for the result? Okay. Basically, this is still quite you still have to test on. You just try to go through several different this result, okay, and see what kind of transformation would be better. And usually, the problem like this, we'll see this. What is this? I forgot where we have that. Usually, this depends on some kind of radial basis function. The reason radial basis function depends on the input vector only through the distance from origin. Okay? So in some sense, this is so if you see different kind of problems, you probably just call for different kind of kernel. Okay. Now you have like a lot of observation for one class lying within like a center or in a sense, okay, surrounded by observation from the other classes. More likely you use this kind of way. So it depends. Okay. Okay. Where are we at? This one. This one. Kernel function used to actually summarize the data, so then do this. Okay. Anyway, there are many in this kernel function. Usually, a low degree polynomial such as this, like this one, okay. All this radial basis function, the kernel work reasonably well. Okay. Usually, this would be the this is good initial time. You just try this type of kernels. Okay. And instead, for this support vector machine classification, is to select kernel, the kernel function to use, and then also set the parameters of the kernel function and the value of the cost. And then we mentioned about C classification problem is what we talk about now. Okay, so set the cost for that, okay. And execute a training algorithm to obtain the alphas. Okay. And unseen data can be classified using on this the alphas of these few vectors, the support vectors. Okay. We already talked about this before. Most alphas i's will be 0, except for quite a few, and these are non-zero alphas correspond to the support vectors. Okay. Now, of course, what we have talked about now is about two classes problem, isn't it? Either in this class or the other class. What about multi-classes? What can we do? Just run in a sense, run several support vector machines. Okay? So use a dummy variables. If you have a categorical predictors, use a dummy variables, indicator variables. Okay? Remember, we can create this indicator variables using indicator matrix in NNet, right? We've seen this. Okay, we used this before. Okay. What was the name of that function again? I forgot about it. In R. It's called IND matrix. What did we use before? Okay. Well, anyway, it's indicator matrix function, okay, from neural net NNet, okay, package. Okay. If you have a multi-class responses cases, there are several ways of doing this. Either use one-to-one, okay, 1 versus 1. Okay. So if you use 1 versus 1, in general you have k choose too many, okay, classifiers, right? Isn't it? That is, you run support vector machines pairwise, right? Pairwise, and you in general you have k choose too many combinations. So k times k minus 1 over 2. That's k choose 2. Okay. You can do 1 versus the rest. Okay. So basically, it's come up with a k classifier. 1 versus the rest means that, okay, you consider one class in particular, and then consider the rest as combined as one another class, and you do this for k classifier. So use either case, then you combine the classifier, either use majority votes, okay, after you come up with these different classifiers, and of course you can always predict the membership of the cases, right? And you can use a majority votes or take the average of the posterior of the conditional probabilities. Here, these are among the strengths of the support vector machine. Support vector machine guarantees to find global max optimum. So local optimum, unlike neural networks, training is relatively easy, and scales relatively well to high dimensional data. Especially you have a lot of inputs, right? And trade-off between classifier complexity and error can be controlled explicitly. You can control that, the cost we mentioned there. And non-traditional data like strings and trees can be used as input to support vector machine. This is kind of strange algorithm. Weakness is, well, of course, choice of kernel, right? So you need to do that, okay? So this part is sort of experimental, and maybe there's some suggestion, like the one that you've seen that, okay? If you have one class surrounded by the rest, then more likely it's radial type of, okay, radial basis type of function. Okay, let's talk about this. We look at the kernels. That will be the last slide. Okay, you can find these different types of implementation of support vector machine, and some implementation can handle multi-class classification. And earliest implementation SVM and this SVM Lite. Okay. Basically, this is a library written in C and C++ by two authors who won the contest. Every year, I forgot which. Yeah, I should have that website data. I think within 1 month, I think you have to come out with the best result. And you compare with others, of course, okay? And see the best you got, right? You're first given with the training data, okay? The test data is not given to you at the moment when you try to train your data, okay? So find out the best training algorithm or training classifier, the classifier in using the training set. And then I think probably last week or so, you'll be given the test data to test on your result, something like that. Okay. And these two authors, the one that I forgot which year they won that competition, okay, which is they give very good result. Okay. And the implementation of the support vector machine now become in R. We have this package E 1071. Okay, implement that. I don't know the reason why they call this strange name of this package E. This looks at first, if you're not told this, look at first, it's like some kind of package there, not so amazing, but it's really nice package. Anyone knows about this? I don't know how this number comes from. Okay, let's see if you can find the history of that. Okay. So package E1071. Maybe this is some kind of version number to this, I'm not sure. So this could be some version 10.71 or something like that. Okay. So this in R implement this lib SVM. Okay. This is some kind of C++ library. This support vector machine. Okay. Here, this is a support vector machine example taken from that this elements of statistical learning network. Okay. This graphics. Among others, at this, it would be nice. I don't have a key to show you which one is actually the support vector machine solution. But anyway, you can see this is nonlinear classifier, right? Okay. In either case, they argue that the training error, okay, will be only 0.18, and with a test error 0.245, and compared to the base error 0.210. Apparently, this is for that data set. This is a really nice result. Okay. Let's look at some of this the kernel functions. Okay. And in that implementation, that library E1071, they implement three. I think basically there are 4 types of kernel function to use. Okay? First, we should say we still have this linear, right? We still have this linear result. Linear result is basically the inner product of XY. So that's our earlier, this in the linear space, the linear classifier. Okay. And you could have this x1. Well, of course, if you look at this one, this is actually a spatial case for that, right? Okay. Where you have zero constant. And I think this is a default in the implementation. The default of the constant is set to 0. Okay, but not the gamma. They have some scale vector here. Gamma is set to 1 over n. I think that's the default. But anyway, we can use help documentation to find it out. Okay. Or you have this monomials of degree d basis in this sense. Okay, monomial. Okay. Okay. So here you have. If you talk about just two numbers, it's monomials in this sense. Because here what we talk about is it's a vector, right? So now is that we can do that. This is among two vectors, okay? You might write in general the monomial, okay? Here is example of monomial with like the three variables here is in this sense some constant has x to a, y to b, okay, b to c, and a plus b plus c is a constant d. So that's called monomials of degree d. Okay? So in that sense, okay. So here, this type of function with this constraint that the exponents of x, y, z add up to d. That's called monomial of degree d. This is not implemented in this package. Okay? And the variation of that would be this. So basically more like, well, the implementation more like this, except that instead of 1, it allows constant, and then there's a scale vector there too. Okay? So you can have various types of polynomial kernels with degree d. Okay? Any of this is of the degree d. Either this type of monomial degree d, and of course, you can say this is a spatial case for that, right? And Gaussian kernel is in this form. This is also, well, in a sense, the first one is also a spatial case of radial basis function. When you say this radial basis function is some function, some function, the function value depends on this x value only through the distance from origin to this vector. So basically, be similar to this. Okay. So x, this is distance. Okay, this is distance from origin to x. Okay, and some allows instead of distance from x to origin, they allow some distance from some certain center. So that doesn't make okay. But you can see this is the first one actually is that kind of result, right? Here this is x1 minus x2. Remember this is like square distance, right? So it depends on this, the difference only to the distance, okay, from origin to this vector. Okay. Radial basis function as well is like this. Okay. I forgot the default implementation radial base. I think the E. Well, we can see that later. So E1071 use this Gaussian, probably the first time. Okay. I already forgot about that. You can see a help documentation of that. Okay. And the third type is a sigmoid kernel base. Sigmoid means S curve, right? That's all. That's all we have. The most commonly known sigmoid function is the logistic function. Okay. Let me put it here. Okay. Sigmoid function basic. Okay. The simple name for that is S curve. That's all. Okay. I'll say S curve. Okay. The most simple one would be this 1 over 1 plus e to minus x. Okay? So logistic function. So you're looking at the S curve like this, okay? And we know that most of the CDF continuous distribution was like some kind of S curve, okay? Because there are many types of this sigmoid kernel. Okay? I should use that. Well, here, basically, this is some kind of constant. Okay? And that that E1071 set this constant as 0 as default for the constant. Okay? And also that they have some constant scale here is gamma here. Okay? The default is 1 over n. They set that kind of sigmoid kernel. Okay? Sigmoid kernel is the one you set to be that default. Okay? The sigmoid kernels can also be neural network. Actually, we've seen that before, right? In the neural networks, the final function form is like some kind of sigmoid types of kernel. Okay, this sigmoid type of function. So anyway, it's best like we look at our example, right? Isn't it? Okay. Use this node 13.r. So here, this is the one we're going to see. Okay. This one is forensic class data again. So remember, you can either use attach or remember I showed you last time you can also use a load workspace. Okay. Load in from whichever data set you have. So here, this forensic class data. This is R data images. Okay. So we can load this in. See, when R working with window, you always see this kind of strengthening here. Okay? If you just try to type this as a command, you don't have to use 2 backslash. Just use 1 forward slash. Okay? So replace every instance of 2 consecutive backslash as 1 forward slash. You want to type it as a command. Okay? So we can load the data this way. Okay? So or alternatively, you can use attach if you want. Okay? You can attach this one, but when you do attach, you will just attach the second folder. Remember, when you do search, right? Search paths of the folder, you will attach the second folder. And if you, I think I mentioned this before. If you load the workspace, you will load to the first folder, so it becomes part of your first folder. That's why you see this F class types, and this part of the first. So either way, okay. Of course, you prefer use attach then. Currently, I didn't use attach, so the second folder is still stats. Okay. Use attach. This will become the second folder. Okay. And the variables will be seen now. Okay, so now let's look at this. This is a support vector machine implementation of that live SVM, okay, implementation in R. So let's run this, require this function, and remember, let's look at the definitions of this kernel function. Okay. Yeah, I didn't exhaust this, and then here look at this help documentation of that. These are the, let me scroll down a little bit. So I mentioned the C classification problem, the new classification problem, right? And the kernel function linear is inner product of the 2 vectors, U transpose V. Okay. Polynomial, we have this gamma. Okay. So here we talk about this polynomial, right? Gamma times inner products of that 2 vector plus some constant of coefficients, okay, raised to power d. I think for this implementation, the default for the degrees is 3. So let's set the 3. This is default. Now you can, of course, you can choose other numbers as well. And the default for coefficient is 0. I think it's spread up there. If you take a look on the other in the degree default to 3. And coefficient default to 0 and gamma. Okay. gamma default to 1 over n, 1 over sample size. Polynomial, and then radial basis would be this minus gamma u minus v squared. So actually, this is our Gaussian kernel, right? So remember this, sort of similar to this, except that we didn't write that one. Similar to this, isn't it? Right? So exponential to some gamma times the square distance. Where are we? And sigmoid use a hyperbolic tangent. So anyway, these are the 4 choices. Okay? If you have linearly separable problems, let's just use a linear kernel. Okay? And usually it's not the case, right? So you call for the other type of kernel as well. Okay. So let's run this. Here I still try to compare with other results. Okay? So here, this require other package as well. Okay. And suppose we do this 2/3, 1/3 split. Okay. It's not the best split that we can come by. You should look at of course, you should look at the glass times. Okay. It's really hard for this one because the minimum number of observations for a particular, what was that? For a particular time is only like 14 observations, right? I forgot about this. You can actually see that. This F glass time, F glass. The last variable is time, right? There's only 9 here, only even very small number of observations. Actually, it is quite ideal in this case using simple vector machine with a small data set. And we even try to do this 2/3, 1/3 split. We're supposed to do this proportionally, right? I didn't do that. But let's say suppose we can try this out anyway. See if this kind of split works. Are we in the danger of having no representations in the training data set? Let's find out anyway. Hopefully this is not the case. So we set this C's and set this indicator. I mean the indices of this one, and then here we have the test set and trend set. Let's look at the trend set anyway. Hopefully you still have good representation of that result. Let's see. Ooh, we have only 2 instances in table. I think that's good in a sense. So here, it takes 7 out of 9 and then 10 out of 13 of that. That's okay. It just happened we have 7 of 9. Anyone is tricky here? This is Star Trek Voyager. There's a particular character called 709, right? Isn't it? Well, anyway, I'm not trying to get into this. Okay, so here we have this training set and test set, and let's try to run this support vector machine. Okay. Suppose we set the cos as 100, okay, and gamma is 1, and this I already forgotten which one is the default. Let's look at the kernel. Look at up there. See the kernel, the default kernel is radial. So it's radial basis function type. So okay. So here we're talking about this type of function. Okay, the kernel function we use in this case, what do we have? Okay. So this is radial basis function types with gamma set at what was that? Okay. Gamma set at 1, so radial basis. So we have this exponential of minus minus u minus v squared. Okay. So we have this kernel function to use. So we first fit this support vector machine on the train set, which cos set at 100. So C set at 100, okay? And gamma set at 1. Okay? So that's why you have that. And let's run this result. And then here, this is a predict function that this is how we predict the class membership, okay, using this predict function right here. So here's support vector machine fit, and then let's also run rpart and this rpart fit, rpart predictor. Let's run several of them. Let's see what happens. Look at the confusion matrix for the support vector machine fit. We have quite errors, quite large error here. 4, 5, 1, 2, 1, 2, 1, 4. That's a lot. A lot of misclassified identities there. And with APER of 28%. It's quite awful, actually. Okay. We can do this. The second one is to give you the same. The second command, so the third command user will just give identity, just sort of a identical result. You want to test on the class agreements, you can use this function, this extractor. Okay. This is 1 minus APER, right? So 1 minus APER, you get this class agreement function. Okay. Extract from the confusion matrix. So next time you want to do that, you can use 1 minus class agreement to get the APER anyway, directly. So. Let's see the recursive partition counterpart of this result. And recursive partition, the error rate is like 41%. Okay. That's a huge number, right? Actually, of course, here we didn't actually fine tune the 3 models. Now let's try other kernel and see what this turns out, and try to C classification based on C classification problem. Bad, right? This is really bad. So sigma actually. Now, in this parameter set, sigma is not really good. Did I run this? Oh, this is rpart, sorry. Okay, I'm supposed to run this part, right? Did I run this already? to run this. You still see a lot of disagreement here, right? Okay. So basically, you can run this. This is even worse, isn't it? The class agreement is only 40-some%, 46%. So actually, that means that you can see that support vector machine, the choice of kernel is really important, right? So it makes a difference. And of course, you also have to tune these parameters. In a sense, in the package caret allow you to fine tune these parameters. Okay? You can use that. What was the command we used before when you use caret training? Use caret function. A function is called train, right? TRAIN, the train function. Allow you to train from different model, including support vector machine. Okay. Use that to train this result. Now here, if you do a tuning of this result, and then assuming that you run, you're going to run this. Run this model with a different parameter range. Now here the commands I use here is that I set the tuning parameters. Okay, gamma was set to from 2 to -1 to 2 to the power of +1. So we do 1/2, 1, and 2, right? Okay, so these are the parameters, and the cos combined with that will be 2 to the power of 1 to 4. So 2 to the power. Okay, so here this would be the tuning parameters on that, and this is still the radio basis function, okay? the default. So let's do this. Look at the summary. Also look at the plot. So here, this is arrow. When you set a gamma at different, remember I said 1/2, 1, and 2, right? So 0.5, 1, and 2 for gamma, and cos we have 2 to the power 1, 2, and 2 to the power 4. So we have all this 3 times 4, 12 combinations of the result, and these are the respective arrow. Maybe I should use more, so then when you plot this, you see a better result. See, on the right-hand side, this is legend for the arrow. Okay. Darker color means that smaller arrow, so that's good, right? Okay. So actually, the idea of this is gamma. The gamma is trying to look for this direction, like roughly, isn't it? So we want to set gamma roughly along this direction. Not exactly. Set gamma at like, for example, 0.9. Or 0.7 right here, and set cos at the 4 roughly, right? To get a better result. Right? So maybe you want to go for that direction with this tuning. Where are we at? You can try this out, okay? And see the result. See what happens. And when you say P, instead of contour plot, you try to plot perspective plot, so sort of pseudo 3-dimensional. Maybe you should try that. Sorry. Okay. So let's try this parameter with this cos 2 to the power -1 to -6 to 1. So let's do that. Okay. Oops. do it. I need the first line of this code here. Okay, so here we have this support vector tuning result. Okay, and then as suggested here, okay, plot this support vector machine tune. Can you see anything from this? You probably need to look at this at a different angle. Or you can use a package RGL to let it rotate and see. Remember, we try to reduce the error, right? The minimums probably occur at the gamma equal 1, maybe, right here. Or maybe there are some points here as well. It should be the smaller one here. This is static class, so really hard to capture which direction we need to go. So gamma and cos. Tune this R part with this function. Okay. Let's look at the result for this. And the parameters we have is the minimum splits of 5, 10, and 15. This is probably not really good. The meaning of this minimum split means that at any node, okay, if the number of observation in the node is below this minimum split, then this algorithm will not split anymore. Okay, so for a node that you ask this algorithm to split is at least the minimum requirement for sample size for that node is like 5. But here we just do minimum split at different numbers here. Probably 5 is not really good. Maybe I should try out. But this is small data sets anyway. Okay. Because when I say minimum split 5, 10, 5, and 5, 3 means there's another parameter setting that the child node should have at least one observation each. Otherwise, we'll not split as well. Okay? That's a default. Okay. Well, anyway, let's see. Let's look at the tune result. Where is that? The optimum minimum speed is probably 10, maybe. Okay, because after that we increase, right? Okay. So we don't want to split to we don't want to split to grow too many terminal nodes. Okay. And with a minimum split at 5, it tends to split more, right? Okay. And with minimum split at 10, split less. So yeah, the base parameter for that probably is a minimum split equal 10. So by default, this R partition R part split at, I think the default minimum split was 20. Okay. If you look at help documentation. Okay. So it requires a node to have at least 20 observations, okay, to split. Otherwise, okay, that node will never be split. Okay, split in that. I really need to stop at this point. I have to go early today, so is it okay?
In case study 3, that's due Thursday, or can we push that back one day?
How about for 5 days, right? Not 1 day.
Oh yeah.
So next Tuesday, right? 1 day means that.
Is that okay with everybody else?
Okay. Well, I think you. Okay. See, I just keep postponing this case study. Well, we end up with only maybe 4 or 5 case studies. We don't have enough time.
So it's due Thursday, Tuesday.
So when did I say Tuesday?
Thursday.
This is the coming Thursday, right?
Yeah.
How about 10 in on next Tuesday?
Okay. Okay, thank you.
Okay.